introduce Taylor Sommerfeld and Melissa Bouts. They're going to discuss the techniques and challenges for material stabilization within historically mitigated underground abandoned coal mines. So, after that.
That's right there. Okay, thank you. My name is Melissa Bouts. I'm with the Brierley Associates, and Taylor Sommerfeld here is with me, and we also have Joel James in the crowd there for us as well. He's up on the screen. This is an Wyoming AML project in Hannah, Wyoming that we're going to be talking about today. And it's a lengthy title, but it does capture what this presentation is about, the challenges that were encountered in stabilizing the materials, subsurface materials, due to mine workings in an historically mitigated area in Hannah, Wyoming. And let's see here. Trying to get that to work there. Radio. So Hannah's location, you can see it's in the southeastern part of the state. And we can zoom in a little bit here. That didn't work. That is definitely not what it looks like. Not a problem. We'll just move right past that. Thanks. So the area we're looking at, Hannah, Wyoming, you can see the mine workings extents. It's a big area. We're looking at that scale bar is about 1.3 miles, so you can get a sense of the extent of the mine workings, miles and miles of workings. But the area of interest is the area in the orange outlined area there. So just trying to figure out how to point this thing here. There we go. Right in here. It's the Hannah number 4 mine, and about 600 acres of undermined area. And most of this, a large percentage of that area is residential and infrastructure. So just a little bit of history with the town of Hannah, 1892. The mining began in the Hannah number 1 mine. This mine had 2 gas explosions within a 5-year period, 1903 and 1908. Tremendous loss of life for such a small community. 228 people died from those 2 explosions. Several years later, we had the Hannah number 4 mine open up, which is the mine that we'll be referring to in the presentation today. And you can see ongoing history. And in about 1960, we start open pit mining began in the area. So you had to transition over to open pit mining. The last mining, or the closing of the last open pit mine, was in 2012. So the current population of Hannah, about 800 people. A phenomenal amount of coal was removed from this area, 220 million tons. The Hannah Basin. So the Hannah Basin, it's noteworthy because of its relatively small footprint and extreme depth of sediments. We're looking at 40,000 feet of sedimentary rocks in the Hannah Basin. But it's in an area that is about 25 miles by 40 miles in dimension. Most basins are an order of magnitude bigger than that have that same depth. So the most analogous one that I can think of is the Anadarko Basin in western Oklahoma. It has about 40,000 feet of sediments as well, but it's significantly bigger footprint. So it's just an impressive situation. And the reason it's like that, it's an intramontane laramide orogeny structural basin. And we have a northeast plunging syncline situation. What we also see is just to compare this basin with other basins in Wyoming, you have the Powder River Basin, which I think is about 17,000 feet thick, and then the Wind River Basin is about 14,000. So nothing really compares to the Hannah Basin in depth of sediments in the state. It's noteworthy. It's also noteworthy because with this steeply plunging syncline, you get a large number of faults within the basin, and that does disrupt the coal seams. And we do see that in our project area. Over on the side here, you can see the stratigraphy here. This strat column goes all the way down into the Cambrian here at the bottom, and the end of the Tertiary up here at the top. And while we do have coal beds in this from the middle to late Cretaceous all the way up to the top of the Tertiary, we are looking at the Hannah Formation here, which is part of the Fort Union Formation. And so we'll be looking just just in here in the next slide. So here we're zooming in on the Hannah Formation. You can see there, I can't remember how many coal seams. Is it 60 some? I know 80 some coal seams, 88, something like that. It's a lot of coal seams in the area. And the darker symbols here are the thicker beds. The bed's thicknesses range from 5 feet to over 40 feet. And in many scenarios that we encounter, all 40 feet were mined. So you're looking at 40-foot thick voids under a town is what's going on here, and other infrastructure. Right. It happens to be the number two bed is the one that we predominantly see mined in the Hannah mine, which is the topic of this presentation. But there were multiple economic seams in the area. A little bit more on the geology. We already talked about the syncline situation in the deep basin. But again, the faults are common. And so here is our current mitigation project area. Generally, our work is currently at least limited to depths of about 200 feet. However, we have been in areas as deep as 300, a little bit more. Yeah. And that's because with the 40-foot thick seams being removed, you have propagation to the surface from those depths. So, but you can see these faults coming through here. There are multiple faults. The one that affects our project the most is this one here along the eastern side. And that's near a football field and elementary school in the town of Hannah that we have mitigated in the past several years. And it just basically displaces offsets the coal, and you got to figure out what's going on in the fault zone. And you can imagine it can be challenging, but that's actually not the main topic of today's conversation. You can see there's the northwest trending faults here, right? As far as the hydrogeology in this area, there are many areas of Hannah that have artesian conditions. The faulting in the syncline within the Hannah Basin has resulted in, you get different pressure regimes across the town. The lowest elevation in the town, the effects of these pressures is magnified, of course. And you can see the effect of those pressures while grouting. It just so happens that in the area of this presentation, the predominant area that we're working in doesn't actually have artesian conditions, but the water is under pressure. And just south of the work areas, we have artesian conditions. We have a discharge well that has been in place since pre-AML work. And that discharge well had been flowing for 40 years, I believe, pretty much nonstop. So artesian conditions are a big deal around here. So even if you don't get the artesian, of course, you do get the shallow groundwater conditions. And of course, as mentioned in a talk earlier today with Dave Hibbard, we get, the mine voids are basically acting as an artificial aquifer. And imagine 40 feet thick of artificial aquifer. It's very intense. The aquifers in the Hannah Formation, they're not mapped. It's just too laterally variable to sort that out. It's just, we have a series of monitoring wells in the town, and we know what the water levels are in those wells, and that's how we sort that out. But here we have a video. Let's see here. I can do this right. Basically, you saw that little PVC sticking out of the ground, and that was in an area outside of the work zone, but just to give you an idea of the artesian flow that we do see in the town. So, all right. So back to the Hannah number 4 mine. We did already talk about it, produced from 1911 and 1941, over 10 million tons of coal. The mine dips at about 25 degrees to the southeast. So you're looking at a very steep dip. The outcrop is just right on this edge of town here, west edge of town. We have the Union Pacific Railroad tracks going right through the area here. And then, of course, the town itself, it's kind of obscured by the mine working map, but you can get an idea of things. You also have pieces of infrastructure, just roads, going through the area, of course, even if there aren't houses in there. Room and pillar mining is the mining method that was employed. Average width of 25 feet. And I mentioned the 24-foot, or it's a 24-foot average height, but we do see rooms almost 40 feet, sometimes even more. So it gets extra complicated when you're next to the fault. Sometimes they can be thicker than 40. And you can see pretty long rooms, the 100 to 500 foot rooms. Pillars were on 25 to 40 foot intervals. Here's a piece of equipment. This is, I believe, the electric shovel, which was kind of a big deal given the time that this was used. I don't have an exact date on this, but we're looking at pre-1941. And so this was an electric shovel used underground in the Hannah 4 mine. And here we have the mine portal with a rail spur connecting to the Union Pacific rail line that I showed in the previous map. All these photos were compliments of the Hannah Museum in Hannah, Wyoming. So as far as historic mitigation background, what we're talking about here is the use of sand slurry. This was a method used in the 1980s to backfill mine voids. It was I believe, started by the Bureau of Reclamation, and it was a preferred method. It was maybe the only method, perhaps, at the time. It was sort of state of the art. And what we found with this, well, basically it's the injection of sand slurry. It's just sand and water. In Hannah, they were able to get the sand from a local source just within 2 miles of the town. And so that was pretty handy. Target zones were down to as deep as 400 feet. And the way they had this set up was with a stationary batch plant right on site. We'll talk a little more later, but this was a very fast project. It was over a 6-month time period that they did this effort. About 800,000 cubic yards, I believe, of sand slurry was placed into these mine voids. And as we'll see later, it really didn't fill a lot of them. So it's just a lot of volume. So this is a general idea of the setup with the sand slurry operation. So you have this hopper, and that's going to be receiving the sand. But right here you have a well. And remember, I mentioned earlier, there is a well south of town that is artesian, even though the actual current mitigation zone is not artesian. The well that I'm showing here was that well that they used for the sand slurry mixing. So they pulled water out of this well here, mixed it in with the sand, mixed it in with the sand over here in the mixing tank, pumped it down into the rooms, and any water that is residual, it could travel back into the EMS well, that well that I was mentioning, or just go back into the formation. So this was the general setup. And this is a map. I'm going back here, sort of zoomed into the town. The outcrop would be back over here. The railroad is south edge of this image. And we have these purple circles, and these represent the volumes, just relative volumes of what sand slurry was placed where. And so the little black circles inside of each of these purple circles, show the injection points. And the thing to remember is that the mine workings are dipping to the southeast at 25 degrees. There's no barrier in place to block this sand slurry and to keep it in any one spot. So, if you're lucky and it goes into a room and it stays in place, that's great. The rest of it could have gone anywhere. Your guess is as good as mine. We do encounter it in lots of places. So the other thing, of course, to just keep in mind, there were certainly areas that didn't get sand slurry. You'll see this method of representing volumes in another slide at the end with grout that we've placed in this same area. This just gives a little idea, a sense of how the sand slurry was placed into the rooms. And so basically you started at the farthest end of the room, drilled your injection hole, and then placed the sand that way, building a cone, kind of filling it. As you go, of course, the flow of water is going this way back to that artesian well that I mentioned. It's the general groundwater flow in that area. These slurry lines were 8 inches in diameter, lengths of up to 4,500 feet from the slurry plant. So, You had initially 25% sand, 75% water in the slurry. As they kind of learned and got a feel for how the process was working, they were actually able to increase the sand to 50% of the slurry. It was an iterative process over the 6 months of the project. So some of the issues with the sand slurry emplacement, really the project was substantially underestimated for the values or the volumes that were needed to be filled. There was no refusal criteria. So we're talking about, with refusal, we're talking about what can we see at the surface that tells us that a void is filled. And usually we'll use pressure nowadays, and I'm not sure what, if anything, was used during the sand slurry process. Joel's shaking his head like, none. Yeah. And that's hence this comment. And so how do you know? How do you know when it's filled? Where's it going? All these things, right? Some of the problems as well. Yeah, and here are some of the reasons, right? The volumes were theoretical, your best guess based on available data. Crosscuts, we didn't really account for those. Those weren't accounted for at all. And the sand's abrasive action on the coal pillars is something that is suspected as problematic with this approach. I think we had 8 to 18 feet per second was the rate of injection, and how can you not be abrading the coal pillars? So a lot going on here. Also, there was no cementitious material in the mix, like just sand and water, so nothing to make it set up. And again, no barriers down dip to keep it in place, and it's going to migrate. It's going to migrate. So here's some stats on that project. It was 6-month construction period, 800,000 tons. Okay, it was tons of granular backfill. So that's the sand itself, not the water, that was in place. Again, within a 6-month period, we had about 100 mine rooms within the Hannon number 4 mine. 25,000 linear feet of drilling. You can see the stats here, but these injection rates I think are pretty interesting. Again, we talked about that in the last slide. Up to 530 tons of sand were injected per hour. That was once the project had gotten into the later stages where they realized that they could actually put double the amount of sand they had originally started in the water and still get it underground. So, when you first started, you were about half of that. And I'm going to hand things over to Taylor. She's going to talk about the current project that we're working on from here on out.
Hello, I'm Taylor Sommerfeld. Can everyone hear me all in the back? I'm a field engineer and I've been working in the Hanna area. We started mitigating this area in 2020, and we're going to continue mitigating. It's ongoing currently and will continue for the foreseeable future. First, what we do is we first characterize the mine workings. And how we do that is we either classify them, we see what the mine interval is. It could either be like an open void, rubblized zones, or filled with that historic sand slurry Melissa was talking about. And then, of course, we come back and we mitigate those risks that we find after we characterize them. Once again, we try to stabilize that sand slurry, or we fill those voids in rubblized zones. And then finally, we come back and we check our mitigation efforts with verification coring or just destructive drilling. As you can see down here, we have a good cementous core there filled with some timbers. And then up here, we have a phenofailing reaction, which helps us identify the grout, and then in contact with that coal layer. So first what we do is we do some drilling, either air, mud, rotary drilling, or some coring to decide what the mine interval is. And we watch that with our drillers and decide what the interval looks like. We also verify those results with a downhole camera. As you can see here, there's the roof of the mine and then sand slurry right beneath it. We also use some downhole geophysics just to confirm our drilling results as well. Some challenges we have is our mine is filled with water. So as you put in material, you're going to get water out. And so a way that this happens that can occur is first, it may pop up in a crack or a fissure that we aren't aware of. This is not the way that obviously recommended or the way we like it. What usually we typically try to have happen is comes out of an existing hole we've already drilled. So this one is a monitoring well. As you can kind of see, there's our transducer right there, and it's just flowing out. And so usually we get about a 1-to-1, depending on where we're grouting, to just displace that water. Over here, we have a situation where we are actually communicating over here, and we're just letting the water flow, and it's actually taking in this borehole right here, and it took water almost the whole season. Sometimes we'll have situations like that where a borehole will take while other ones will give, and so it's kind of moving around and deciding what works on the project. Additionally, in the mine, we have water, but we also have that historic sand slurry, which also is highly mobile, which is why it's moved down dip so much. So with that, we get, let's see if this video will work. Yeah, so with water will come out the sand slurry. So you can see in this video, water and slurry are both coming out. And this can happen in this, it's a lot of water in this video, and it can come out that sand slurry is much thicker, and this year we've kicked out a lot of sand slurry this year that was very thick and had to just truck it off. This other video here is a downhole camera video. You can see it's kind of bubbling. It's just showing how mobile it is. Also, what I want to point out is you can see where that coal is in contact with that sand slurry, meaning that whole mine region is filled with that sand slurry, which causes difficulty with grout injection because we can't get our injection pipe all the way down the mine, which causes some difficulty. Another thing is while we are injecting our sand slurry into it, it'll take for a good day, and then we'll come back the next day, and that sand slurry will rebound far above the roof. That also causes some difficulties just because it's so mobile. So our end goal with the sand slurry currently is just trying to consolidate it, pushing it to different regions where we're grouting, and just making sure it's pressured up and sucking in the area. Another one of the final issues is just the mine geometry itself. As you can see here, we have our rooms. We have kind of our ventilation plane, which is down on dip, and cross sections between the rooms. As Melissa said, the mine is dipping about 25 degrees. They mined around 20 feet of it, leaving a bottom layer and a top layer. Sometimes we will see it go higher depending on how far they go up, or if it's rubblized, we may even see higher regions that we need to mitigate. This is kind of that cross-sectional view. So like there's a room, there's our cross cuts. So while mitigating this, our injection borehole will pressure up. So this is a John Lutz output of our pressures that we get. And so we'll pressure up and we'll try to hit our criteria. But as you can see is we may hit our pressure criteria, but we might have void space because we're not exactly at the top of the interval. So the best way we can do that is try to get our pressure criteria all the way, but also verification drilling is really important in this situation, just to make sure we do get all those little spots as well. This is kind of a map of like the one that Melissa showed of sand slurry, but this one's the grout injectors we have placed in. It doesn't have the ones that we have this year, so we've injected in this area this year. And this kind of just show you the vast area that we're working with and what we've done so far. And once again, these circles, that's kind of where we injected and just an area around it, but it might have moved down dip, it could have moved up dip. It's really just a visual interpretation of where we placed material. One issue in Hannah is we do have this mobile sandy area that lies right beneath bedrock. And if the drillers are not accustomed to it and know that it's going to be happening, usually what we have to do is we drill with mud, or we put the alluvial casing in deeper. But if it's in an area that we weren't quite expecting to hit it, it may cause these tension fractures, and just because it's so mobile. And worst comes to worst, we may eventually have a washout sinkhole subsidence like these ones. All right, and then so lastly, just kind of to go over it, is that sand slurry has moved a lot, and we're still dealing with it and trying to consolidate it. The project is continuing to develop as we're grouting. We're consolidating that sand story more and more, and it's becoming more of a bigger deal. We're adapting our different methods and things like that. And verification is very important for those voids, and especially to make sure that sand story is consolidated. And there's still a lot of work to be done. So